Welcome to another module in this massive open online course on Bayesian MMSE estimation for wireless networks. And previously we have seen that the MMSE, or the minimum mean squared error estimator of an unknown parameter h, is given as the expected value of h given y bar, where y bar is the observation vector. So we have seen in the MMSE estimate of this parameter h is basically expected value of h given y bar, right. H is the unknown random parameter, correct. This is the unknown random parameter. Y bar is the observation vector, and MMSE, of course, this stands for the minimum mean squared error, correct. This is what we have seen so far. MMSE stands for the minimum mean squared error, all right, and this is an important aspect of the estimation. So let us now illustrate how to compute this MMSE estimate for a Gaussian scenario, all right. So what we want to do is today's module is that we want to compute this MMSE estimate specifically for a Gaussian scenario, or basically when the parameter h and the observation y are jointly Gaussian. So what we want to do is we want to compute MMSE estimate for a that is, see what this MMSE estimate looks like when the parameter h comma observation y, we are not considering we are considering a single observation y, when the parameter h and observation y are jointly, and this is important, when they are jointly Gaussian, that is h, that is the random parameter h and its corresponding observation y are jointly Gaussian random variables, all right. We want to compute the MMSE estimate for this scenario, which is nothing but the expected value of h given y, all right. So to start with, let us consider zero mean random variables, that is, let us say that expected value of h, to make things simple, let us consider expected value of h equal to expected value of y equals 0. This basically implies that the parameter h and the observation are zero mean random variables, all right, they have zero mean. Also, let the variances be given as expected value of h square, which is the variance of h, since it is a zero mean random variable, equals sigma h square, that is the variance of the parameter is sigma h square, expected value of y square equals sigma y square. This is the variance of the observation. So let us write this down. This is the variance of the parameter. This is the variance of the observation of your observation y, or rather this is the variance of the parameter and this is the variance of the observation. Okay. And also we need the covariance, that is, we need the expected value of h times y, right. We need the covariance, that is expected value of h or rather the cross covariance expected value of h y, which we will denote by rho sigma h into sigma y, where this rho is, you might already be familiar with this rho is the correlation coefficient of the parameter h and the observation. This is the correlation coefficient of the parameter h and the observation y, that is, this correlation coefficient is defined as rho. It can be seen that the correlation coefficient is given as rho equals the cross covariance expected value of h y divided by sigma h into sigma y, that is a product of the standard deviation. Sigma h square is the variance, sigma h is the standard deviation of h, sigma y square is the variance of y, sigma y is the standard deviation of y, which can be written as expected value of h into y divided by under root sigma x square sigma y square, which is nothing but basically that is rho equals expected value of h times y, sigma h square is expected value of h square and sigma y square is expected value of y square. So, this is the definition of your correlation coefficient. Remember, this is rho, which is the correlation coefficient. And one of the most important and interesting properties of the correlation coefficient is that the magnitude of the correlation coefficient is always less than 1, right. It lies between -1 and 1. It indicates the extent of the correlation between h and y, all right. And of course, for Gaussian random variables and h and y, this is also something that many of you might be familiar with. For Gaussian random variables h and y, if the correlation coefficient is 0, right, for any two random variables h and y, if the correlation coefficient is 0, then the random variables h and y are uncorrelated. However, for Gaussian random variables, that is jointly Gaussian random variables h and y, if the correlation coefficient is 0, then h and y are independent as well. This property holds only for Gaussian random variables h and y. Okay. See, these are some of the properties of the correlation coefficient. Okay. So, now we want to come up, remember, we want to come up with the MMSE estimate of h given y. So, towards this end, first we want to construct the joint distribution of h and y. Okay. So, let us look at this vector, let us define this vector, let us construct this vector. This is our vector, which has basically the parameter and the observation. And what we want to come up with is, we want to come up with the joint density or the joint probability density function of h, the parameter h comma the observation y. Okay. So, towards this end, let us define the covariance matrix of this vector as expected value of this vector times its transpose. So, we want to define the covariance matrix R as expected value of vector h y times its transpose, which is the expected value of this matrix which is, now you can see h square, h y, y h, y square. Okay. And expected value of this is, now let us look at it, let us take the expected value of each term. Expected value of h square is, of course, this is sigma h square, expected value of y square is sigma y square, expected value of h y is rho sigma h sigma y, expected value of y h is rho sigma h sigma y, and this is the covariance matrix of the random vector h comma y. So, what is this? This is the covariance matrix. This is your covariance matrix of the vector h comma y, where h denotes your observation and y, h denotes the parameter and y denotes the observation. All right. So, we have defined, or we have rather derived the covariance matrix of the vector h y, where h denotes the parameter, y denotes the observation, all right, in terms of the variances of h y, and also the cross covariance, that is the cross correlation between h and y. Okay. And of course, we also need R inverse, that is the inverse of this covariance matrix, and that is given as follows. That is the inverse of this matrix sigma h square sigma y square rho sigma h sigma y rho sigma h sigma y inverse, and that is given as 1 over the determinant of this matrix R. This stands for the determinant times the inverse of this 2 cross 2 matrix, basically where we interchange the diagonal elements sigma y square and the negative of the off diagonal elements, right, minus rho sigma h sigma y. This is the inverse of the matrix. Of course, we can also compute what is the determinant of this matrix R. The determinant of this matrix R, you can see, is basically sigma h square times sigma y square minus rho sigma h sigma y times rho sigma h sigma y, which is basically your sigma h square sigma y square minus rho square times sigma h square sigma y square, and this is equal to 1 minus rho square sigma h square sigma y square. This is the determinant of the covariance matrix. This is the determinant of the covariance matrix. All right. So, now remember the LMMSE estimate of the MMSE estimate is given as an expected value of h given y, expected value of the parameter h given the observation vector y. For that, we need the conditional probability density function of h given y. Okay. So, we need to find the conditional probability density function of the parameter h given the observation y. That is, we need to calculate the MMSE estimate, which is basically expected value of h given y. We need the conditional PDF f of h. We need the conditional probability density function of the parameter given the parameter h given the observation y. Okay. Now, the conditional probability density function, we know that this conditional probability density function f of h given y, and this is important, the conditional probability density function of h given y this is basically given as the joint probability density function of h comma y divided by the marginal probability density function of y. All right. So, this is the important relation, this is the relation, is an important relation to keep in mind, and this is the relation we are now going to use to compute this conditional. Remember, this is the conditional PDF this is the joint PDF of h comma y, and this is the marginal PDF. This is the marginal PDF of your observation y. All right. So, we can compute the conditional PDF of the observation h of the parameter h given the observation y from the joint probability density function of h comma y, all right, divided by the marginal probability density function of y. All right. So, we need to compute each of these components. All right. Now, first we know the marginal probability density function of y. This is easy to compute. What is this? We know that y is a Gaussian random variable. Expected value of y equal to 0 and expected value of y square equals sigma square or equals sigma y square rather. So, y is a Gaussian random variable with mean 0, variance sigma y square, which implies f of y equals 1 over square root of 2 pi sigma square e raised to minus 1 over twice y square divided by sigma y square. I can also just write it denoting this e as exp. I can also write this as 1 over square root of 2 pi sigma y square x minus y square divided by 2 sigma y square, where e and x are basically one and the same thing. E raised to x is basically exp of x. Okay. So, the Gaussian probability density, the marginal probability density function of this Gaussian random variable y with mean 0 and variance sigma y square is 1 over square root of 2 pi sigma y square times x of minus y square divided by 2 sigma y square. Okay. So, that is the easy part. Now, we want to come up with the joint probability density function of h comma y. So, what is my question is now, or I have to rather find the joint probability density function of h comma y, and this is given as, this is slightly complicated expression, this is given as basically, let me write it down and then you can see what this is. This is given as 1 over square root 2 pi, 1 over square root 2 pi square determinant of r x or e to the power of minus half h comma y or the row vector h y times r inverse times the column vector h y. All right. This is basically the joint probability density function. This is the expression for the joint PDF of h comma y, which is in fact Gaussian, right. H comma y are jointly Gaussian random variables. Okay. So, this is the expression for the joint probability density function of the jointly Gaussian random variables h comma y, where h is the unknown parameter, y is the corresponding observation. All right. So, now let us evaluate this joint probability density function of h comma y, and this, to evaluate this, first we need h r inverse. We have already calculated r inverse. Now, let us evaluate what is h y, what is row vector. I want to evaluate this part. that is the row vector H y times R inverse times the column vector H y, that is the row vector H y. We know that R inverse is 1 over the determinant of R, which is sigma h square sigma y square into 1 minus rho square times, well, sigma y square sigma h square minus rho sigma y sigma h minus rho sigma y sigma h times the column vector h comma h y. Okay. And this can be simplified as, now this is a scalar quantity. So, I will bring it up front. So, this is 1 over sigma h square sigma y square into 1 over 1 minus into the row vector h y times this matrix, which is sigma y square sigma h square minus rho sigma y sigma h minus rho sigma y sigma h times, well, let me write it over here, times the column vector h times the column vector h y, and now I can simplify this as 1 over, let me simplify this, I can simplify this as 1 over, well, I can simply write this expression. In the denominator, I have sigma h square sigma y square times 1 over rho square. In the numerator, I have h square sigma y square plus y square sigma h square, that is I am evaluating this part over here. This is the part which corresponds to the numerator, which is h square sigma y square plus y square sigma h square minus 2 rho sigma h sigma y times h into y. Okay. So, this is basically the term which corresponds to the row vector h y times R inverse, where R is the cross covariance matrix, right, or R is the covariance matrix corresponding to the vector h y times the column vector h y. Okay. And therefore, the joint probability density function is given as, remember we go back to our earlier relation for this joint probability density function. So, the joint probability density function that can be obtained from, remember this relation that we have over here, that gives the joint probability density function, and therefore, that is now f of h comma y of h comma y, which is equal to now 1 over 2 pi square determinant of R times e to the power of minus half, okay, e to the power of minus half, the denominator I have sigma h square sigma y square into 1 minus rho square. In the numerator, I have h square sigma y square plus y square sigma h square minus 2 rho sigma h sigma y h comma y. Let me just write this clearly, minus 2 rho sigma h sigma y times h y. Okay. And now, I can substitute this value corresponding to this determinant of R. We also know what is the determinant of the covariance matrix R, that is 1 over, let me again write this clearly over here, that is 1 over 2 pi whole square times the determinant of R, this is basically 1 minus rho square sigma h square sigma y square times e to the power of minus half basically sigma h square sigma y square into 1 minus rho square, and on the numerator we have h square sigma y square plus y square sigma h square minus 2 rho sigma h sigma y into h comma y, and this is therefore the joint distribution. What is this? This is my joint Gaussian this is the joint Gaussian distribution of the parameter h and the observation y. Okay. Now, we have the joint distribution of h and y. So, we have two aspects, we have the joint distribution, this is your joint distribution, we have the marginal probability density function. Okay. So, this is basically your marginal probability density function of random variable y. Now, we substitute this joint distribution and the marginal distribution joint probability density function of h comma y in the numerator and the marginal probability density function of y in the denominator in this expression to get the conditional probability density function of the random variable or the parameter h given y. Alright. So, once we get the conditional probability density function of h given y, we can evaluate the mean of this conditional probability density function to derive the MMSE estimate of the parameter h given the observation y. Alright. And that is something that we are going to do in the subsequent module. Alright. So, we will stop here.